Page 2 of your big blue book of parent functions features the absolute value function. So we're looking at a piece that's built from two different lines, so it's sort of connected to linear. You studied the absolute value function before. You may or may not remember a whole lot of it, but just taking a look at the graph, you obviously can put in any value for x. So the domain is from negative infinity to infinity, all real numbers. The range is more like the parabola. More like a parabola. You notice that y can never be negative, so y has to be greater than or equal to 0. It can be equal to 0. And because it's greater than or equal to 0, the interval notation version of this is it starts at 0 and goes to infinity. 0 has a square bracket because 0 is included. That's the equivalent of the greater than or equal to version. Infinity has a curly bracket always because you can never be equal to infinity. You never get to infinity. You can just get closer and closer and closer every time. You notice that there's an intercept at 0, 0. The origin is both the x-intercept and the y-intercept. There are no asymptotes. The key points here, -1 and 1, 0, 0, 1, 1. If you know what happens to those 3 points, you can basically graph the entire function. It is symmetric, as you notice, symmetric over the y-axis, which makes it an even function. There's more information on even and odd functions if you don't remember what an even function is. It is not a one-to-one function because even though each x has one y, most of the y values have more than one x. So for y equals 1, you've got x could be -1 or 1. For y equals 3, you could have x equals -3 or x equals +3. Either one of those would get you to the same y value. So it is not one-to-one. It is, however, continuous. If you draw this, you can draw the whole thing without picking up your pencil. So yes, it is continuous on the entire domain, negative infinity to infinity. The end behavior here. As x goes to infinity, we're heading out this direction. As x goes to infinity, we're heading out this direction. Y is also going to infinity. As x goes to negative infinity, we're heading out this direction. X goes to negative infinity. Y is also heading toward infinity. So as x goes to infinity, y goes to as x goes to positive infinity, so does y. As x goes to negative infinity, y keeps going to positive infinity. Y goes positive in both directions. Looking at the graph, you can see it does not have a maximum. It just keeps on going up forever and ever. It does, however, have a minimum at its vertex, 0, 0. So no maximum, but it does have a minimum at 0, 0. You notice also, we're talking about left to right when we talk about increasing and decreasing. As you start on the left, we're decreasing. We are going down until we get to 0, 0, at which point we start increasing. So it's increasing when x is less than 0. That's also known as the interval negative infinity to 0. So you can write that in either way, as an inequality or in interval notation. Sorry, that's where it's decreasing. It is decreasing on this interval. It is increasing when x is bigger than 0, also known as the interval from 0 to infinity. There we go. Make sure you get that right in the way that I did not get it right. So we're good. Increasing x when x is positive, decreasing when x is negative. It's coming down, it's going up. There aren't many special alternative forms of the absolute value function. You don't have to worry too much about that. But it does have some applications, especially basically things that have to be positive. Distance is often used with absolute value. The distance from your house to HB is the same as the distance from HB to your house. It always comes out positive. Or if you're talking about the difference between two quantities, how close are you to a target goal? You know, you might be $10 away from that target goal, and it doesn't matter if it's $10 before or $10 after, but it's still positive. It's a positive difference. So there you go, absolute values. Enjoy.